Okay, so we have our boxes and items chart, and if you haven't already watched the general video going over how to use that chart, do that first. Just going to go through several specific examples here. You may want to, in fact, I'd strongly recommend that you pause the video before each one and see if you can figure out what the boxes would be, what the items would be, if it's in this chart, where we would find the answer in this chart, and then play the video and see as I go over it. So let's start with number 6. We have each of 35 middle school students on a class trip must declare his or her first choice for a lunch stop. Choices are, we got 4 different choices, and how many different ways can the preferences be made? All right, so we need to think boxes and items. Are the students the boxes and the things the items, or the things the boxes and the students the items? Um, if you're trying to start off, n is usually greater than or equal to k. There are maybe exceptions we could talk about in certain cases, but um, let's give this a try first. So that would mean, we have 4 different places to eat and we have 35 students. Let's see what that looks like and see if it makes sense in this case. So this is Arby's, we have Subway, Taco Bell, and good old Mickey D's. And we have 35 middle school students. So let's see what it looks like if we consider the students as the items and the restaurants as a place. So say we start with Alan, and Alan chooses a place to eat. Say Alan likes Subway, so we put Alan right there. And then we have Bernice. Bernice likes Taco Bell, put her right there. C, I'm just trying to, Carl. Let's say Carl also likes Subway. And so we continue like this. We have 35 different, we'd run out of letters, but I'm sure we could recycle Alan and Alice, for example. Um, so we have to check, does this fit? Well, this makes sense. This makes sense that, as soon as a student chooses, we put them into one of these 4 categories. Um, are we allowing empty boxes, which would be right here, or are we not allowing them? Well, it looks like there's nothing preventing one of these restaurants from not being chosen. Maybe none of the 35 have McDonald's, and that's okay. So that would mean empty boxes are permitted. So we're talking about 35 middle school students. So n equals 35, k equals 4. Looks like the middle school students themselves, um, assuming we're considering them as different people here, would be distinguishable items. And then the boxes, which are the restaurants here, they're also distinguishable. If A likes Subway and C likes Subway, that's different than A and C liking Arby's. So we're distinguishable there. And we're saying that empty are allowed. It's okay that McDonald's doesn't get chosen at all, for example. So that puts us right here. Our K value is 4. Our N value is 35. So that would be our answer. 4 to the 35th different ways for the preferences to be made. All right, number 7. We have 24 bars of soap of the same brand, size, packaging must be placed into 15 unmarked equivalent boxes. Um, so we have N equals 24, K equals 15. And again, we're just going to try it out with N being the bigger one, and we can decide if that makes sense when we get our final answer. Each box must contain at least 1 bar of soap, so we're in situation A there. Our items are undistinguishable, same brand, size, and packaging. So this is indistinguishable. Just gonna put it like this. The boxes they're putting them in unmarked equivalent boxes, which means they're also indistinguishable. So we're looking for indistinguishable items, indistinguishable boxes, and not allowing the empties. So the answer here would be partitions of, so our n value was 24, k value was 15. And if you wanted to draw a picture there with the 15 different boxes and then starting putting the soap into those boxes, you could certainly do that. 40 Tootsie Rolls are distributed between 7 trick-or-treaters. Okay, so we're going to let n equal 40 equals 7. However, not all the children like Tootsie Rolls, and some may unexpectedly refuse them. How many ways can a distribution be made? So we're saying empty are okay here. The children here are the boxes, or you could think about them maybe as having bags that they collect the Tootsie Rolls in. But either way, it's situation B. These Tootsie Rolls are indistinguishable, whether I put the first two in Happy's bag or Sneezy's bag and one in Dopey bag. It's not going to matter if I put the first one in Dopey's bag and the next two in Happy's. The Tootsie Rolls themselves are indistinguishable, whereas the dwarves are distinguishable. So if Sneezy gets 7 and Dopey gets 3, that's different than Dopey getting 7 and Sneezy getting 3. So this puts us indistinguishable items, sort of over here, distinguishable boxes right here, and part B, so we're looking right there. So we're dealing with combinations, n plus k minus 1, 40 plus 7 minus 1, and then k minus 1 would be 7 minus 1 gets 6. So 46 choose 6 different ways to distribute these Tootsie Rolls into the dwarves' bag, basically. All right, 9, we have 100 $1 bills to his 4 children. How many ways to do this, assuming each child has to get $1? What if there is no restriction? So if either way, we have n equal 100. These are the dollar bills. Notice they're all the same. So these are indistinguishable. It's not like we're looking at the serial number. We just care. The kids don't care what the serial number is. It's more how many dollars did you get, basically. And we have 4 children who certainly are distinguishable. In general, people are going to be distinguishable unless there's something very, very specifically worded to count them as identical people. That would be very rare. And if each child must get at least $1, well, that's A. So the first one here would be indistinguishable items, distinguishable boxes are A. So this would be C 99. K minus 1 is 3. And then part B, still going to have 100 indistinguishable. You'd have 4 distinguishable children, but now you're allowing empty if they don't revolt against you for such a atrocity. So in that case, we're going to be same place, except we're going to be back down here, the bottom. So 100 plus 4 minus 1 is 103. And then k minus 1, 4 minus 1 is 3. So we have 99 choose 3 for the first part, first question, and 103 choose 3 for the second one. Okay, let me do 10 at least here. How many positive integer solutions are there to the equation? This one starts to get tricky. And I'm just going to go through the answer and maybe talk a little bit about it. But really what we're doing is we're distributing these 100 ones. You can think about ones. Why ones? Well, because we're talking about integers and positive. So it's not like one can have negative 10 and the other has positive 110. We have to make sure we're only getting positive integers. And so this right here is 100 is our n. And they're indistinguishable. These ones, anytime you deal with a number and you're breaking it apart like this is indistinguishable ones, I guess you could say. The boxes, what are the boxes? Well, there's value, 9 different specific x values. So our k here would be 9, and these are distinguishable. Why? Because if you had 7 for x1 and 3 for x2, that's different than 3 for x1 and 7 for x2. Because they're numbered here, that makes them distinguishable. Are we allowing empties? Well, it depends. These x values, is it okay for some of them to be 0? It's not, because we say positive integer. 0 is not a positive integer. 1 is the lowest positive integer, which means each of these values of x has to end up with at least one of the ones. So we're saying each box must be non-empty. So we're doing indistinguishable items into distinguishable boxes. We're back here, part A, because we're not allowing empties. So we have C, 100 minus 1 is 99. 9 minus 1 is 8. So we end up with 99 choose 8 ways to solve this equation into those 9 positive integers where the specific values are different. X1 is different than x2 is different than x3. Okay.